Welcome all. So last labs we have seen how to interface the built-in LED switches and everything with the SoC. Now we will see how to create a custom module and how to use it in your block design. So in the previous project you can see that we have only one block design source in the Vivado code. So let me select my project folder. So this is about an 8-bit multiplier, my mul 8-bit let it be. Okay. So my board is ZC102. Okay, so in the previous works, coming to the Vivado environment, you have only one project folder and you have only one source file. Your only source file was a block design. But from this lab, we will be having probably one more verilog module. So in this project, I am creating a design source. So let me create a new file, a mul 8-bit finish. Okay. So in the design source, you can see your verilog code. So I'm planning to have a simple multiplier here, right? So I have a code with me right now. Okay. This mul underscore 8-bit was my module name. You have two inputs, A and B, and one result. That's it. It's a simple combinational thing, just assigning the result as A into B. So you have two 8-bit inputs, and the result is maximum say 16-bit. That's all. Okay. So this is your verilog module. It's a multiplier. Now I want to create a block design in which I have to include this module. So you can do it in two ways. So today's lab we will directly use this particular module directly in the block design. Another thing is you can package it to an IP. So we will see that method in the next lab. So in today's lab we will not be packaging our IP. We will not be creating any custom IP, but rather I will be using this particular module directly in my IP design. So I am going to start an IP design. So this is the major difference from previous projects. There we had only the block design. Now you have the block design as well as the verilog code. So adding my sync SoC, going for block automation for applying board presets. Right. Now let us connect our GPIOs. So how many GPIOs are required? You need probably 3 GPIOs, 2 for the inputs and 1 for the output, right? So I'm just copying and pasting it, right? Okay. So GPIO 0 is for say first input, GPIO 1 is for the second input, and this is for the result, right? So let us configure GPIOs first. So previously we used the configuration like this. We use switches and LEDs. Now it is custom. Now how many bit should be GPIO 0? I am reading an 8-bit input, so its width is 8. Now this is GPIO 1. This is for the second input. Again it's custom only here, and again it's an 8-bit data. What GPIO 2 should do? It should read GPIO 0s and 1 will pass the data to our particular multiplier module. We will place it here, and the result will be available through GPIO 2. So he has to read a 16-bit data, maximum say 16 bits. Okay, you can see the width over there. These are 8 bits. So you have this input output marked over there, right? So this is again 8-bit, and the result you can see here, it's 16-bit. Okay, we will be connecting to the input over here because he has to read from the multiplier module. Now the thing is how you can add your multiplier module. So if you look at the I'm using control I shortcut. If you look for multiplier, you don't have the custom. There is a default multiplier, but the multiplier which we have created, that is multiplier 8-bit, that will not appear here. So that will appear here only if you are creating the package. We will use that from the next lab. So here just right click on your block design. There you have the option to add module. Now we were using add IP still now you can go for add module. So your module which is available in the project will appear here. So we are in the same project. That's another important point to keep in mind. You are in the same project, you have this module as well as your block design. So your module has been added here, right? So I'll place it here. So you have two inputs and one for the output. So how can you connect this? You have to see, this is the first input. It should be connected here. It is not showing any valid connection here, right? So let's see that. If you expand it, you can see that this fellow has to pass this 8-bit data to this, right? So it's a valid connection. You can see this. Now here also you expand it. This is the second data that will be out from your GPIO and into the multiplier block. Now the result, again I am expanding the GPIO to, so the result will be 16-bit data. Here you can see where his tool is suggesting where it could be connected. So it should be to the input of your GPIO, not to the output, input of GPIO. So this is the connections that you have to do manually. Now you can go for connection automation. Right. So something is missing. Again, you can go for the remaining connection automations. Let me rearrange it at a click. So everything is done. Okay, you have an interrupt left over there. And one more thing you can notice that axis, you have two axes. That's enough because axis interconnect will take care of this three in the sense two input and one output. Okay. Now the thing is you have to validate the design, right? Let's validate it. So validation is successful. So we are done with the hardware. So once again back to the hardware, you have the sync SOC. This is for the processor reset systems. Reset will from the processor, reset will come here and it flows to all other modules. Okay. So since my multiplier is simply a combinational network, it is not having any clock or reset. If reset was there, it will be connected there also, right? Now axis interconnect, your GPIOs 0 and 1 for input and 2 for the output. That's it. This is your multiplier. You can see the barging of RTL over here. Rest of the blocks you don't have that, right? Because they are IPs. They are your IPs. If you were using multiplier underscore 8-bit IP, if you are packaging that module to IP, you cannot see this barging here. Okay, so this is how you can identify your verilog module. So that's it. So now we will go for bitstream generation, means synthesis, implementation, and bitstream generation. Everything will happen in a click over here. So I'm saving my block design and just running that. So let it get completed. We'll wait for that. So the bitstream generation failed for me. It didn't create the HDL wrapper, right? So two things you have to keep in mind. Creating HDL wrapper, that's fine. But the modules that you are creating, it should not be the top module. Sometimes if there is an option like set as top. Okay. So somehow if this module is, if not this module is not the top module, you have to set it as the top module, right? So now here in my case, I need to create the HDL wrapper. Without the HDL wrapper, we tried for the bitstream generation. So I am creating HDL wrapper. So once you are done with your block design, you must ensure one point. Your block design should be the top module. Okay, in this project you have the block design and the verilog code. Always this should be the top module. If it is not the top module, right click and make it as the top module. Okay. Otherwise, what will happen? This fellow will be the top module. If this fellow is the top module, the issue is that uh, he has input and outputs. So he has some pins. He needs some pins. So when you go for the synthesis, there will be error because the pins will not be assigned. So you have to write the constraint file also. But our top design is the block design which is not having any input output pins, because input to the multiplier that flows from your SOC. Okay, in the sense your PS. Okay, it's not coming externally, it's from the PS only. So always remember to keep this fellow as the top design, and I'm creating the HDL wrapper. So HDL wrapper is done. So you have your Verilog code for your hardware and your Verilog code for your multiplier, right? Now we can go for bitstream generation. So it will take some time. We will wait for that. So our bitstream generation is completed. Not interested in the reports and all. I'm not opening the implementation. So once the bitstream is generated, you can export your hardware. So I'm including the bitstream. Now I'm saving it in the same project folder. Finish. So once your hardware is exported, you can switch the platform to Vitis. So you can launch Vitis from your Vivado itself. Launch Vitis IDE. So I'm interested in keeping the project files in a separate folder. So for the Vitis code, I'm creating another folder. As I mentioned earlier, don't give any space in this, otherwise it will create path error. So here you can see the design one wrapper file. So if you look at the project source file, you have the source file for your block design as well as the Verilog code. So this is your Verilog code and this is your block design. Okay, BD file. So this project you have both sources, and this is your project file. This is your hardware.xsf file. Now the Vitis part will be saved within this empty folder. Now let's launch Vitis. So you have to select that particular folder. So mul 8-bit Vitis code. Okay. So this is the folder where I will be having all the project file associated with the Vitis. So I'm just launching my Vitis. Now what you can do, you can create the application project. Next, so you have to select our custom hardware that we have created. So that was saved in this particular folder. Design one wrapper.xsa, that was my hardware. Fine. So click on next. So as I mentioned earlier, you have quad core and dual core processor in this board. I'm using the quad core and the first core of that. You can give some name for your application. Selecting empty application, click finish. So now you need the C code in your Vitis. So what we have to do over there, you have to pass two outputs from the Vitis PS. Okay, that is actually input to your multiplier, and the result will be returned by the multiplier. So you have to read it to your PS and display in the serial terminal. So in the source file, I don't have any source code, so I'm adding one. So this is your 8-bit multiplier source code .c. You should give .c extension. Okay. So I have already coded it somewhere here. Okay. So this is the code. So let's look into the code. So as I said earlier, you have the xparameter.h. So if you open the xparameter.h, here you have to find your GPIOs. Fine. So you can see here you have three instances now. Three instances of GPIOs. 0, 1 and 2 are the device IDs. So you have the base address for each and every GPIOs here. So from the block design, just identify your GPIOs, because we have to distinguish between inputs and outputs. So 0 and 1 are your inputs and GPIO 2 is your output. Okay. So in your C code, say input 1, I am defining a variable input 1, so that is GPIO 0, and input 2, that is GPIO 1, and the output is GPIO 2. So as per your block design, you give your base address. So from where you will get this value again, that is from the xparameter.h. Here you can simply copy this base address, or you can directly type also, because Vivado follows this particular pattern: x bar x parameter underscore axi underscore GPIO, it's everything same, underscore your device ID, this is 0, 1 and 2, and base address, everything is same. You just want to change the device ID, that's all. So you can either copy or type it manually. And I need an integer to store the result. Okay, I don't need any integer to store this input 1 and input 2, because you are not storing that anywhere. We are just in your C code, you can see that you will be just sending it to your PL. Okay, or your axi, you can say directly, because PS is, he don't know anything about your module. He will just write it to the memory, to this particular base address. So I'm just initializing the platform, then just giving some header just to recognize or troubleshoot. So you can open the serial monitor also meanwhile. Okay, so this is how I did that window show view. I have just typed there serial. Now I'm just turning on my board. My board is connected to COM7. You can identify it from the device manager. This is the board, right? Okay, so it's connected. Now this is the basic part of the code. We have only 3 lines. First line is zil out 8-bit. I'm just sending the first data. You can give any data. I'm giving the maximum one, 0xff. It's 8-bit data. So ff, I'm passing ff. This is the first data, first input. So this will be fed to your multiplier module. And second one is again ff. I'm trying the maximum multiplication. So that will be fed to the input 2. And you will get the result. From where you will get the result? You have to read it. Your multiplier module will calculate this, and it will be read by the GPIO 2. So GPIO 2, I have defined another variable output. So this particular GPIO, that variable is referred as output. So that output will be read by this function and will be assigned to the variable result. So result is an integer value. Okay. Now I'm just printing the result. So zil printf function is used, result. So I'm printing in hex. You can print in any format. So ff into ff. Let us see the result in calculator, and let's verify that here. So result will be printed over there. Okay. So that's it. Now let us try to build this project. Build project. Once building is complete, we will program our FPGA. So not only FPGA and the PS. Okay. So when you click run configurations, 2 things will be happening. Your PS will be programmed, as well as your PL will be. PL is your FPGA. Both will be programmed. So if you look at the project folder in the Vitess code, now this is your application. You don't have any debug file here. Once your build is completed, you can see your debug file. So build has been finished. There was some error, right? Mul 8-bit SRC, you have some error. We'll try to troubleshoot it. Platform.h, okay. It's concerned with platform.h. So you can do one thing, clean platform, again neglect it, or you can add this header to your project folder. Okay, so initialize and clean platform. I'm just neglecting it. Now I will try to build it again. If you want to keep this particular header, you can just copy that header file from any other folder and keep in your project folder. So its build has been finished. Now let us look at the project folder. Here you can see the debug right now. Okay, so here you have the ELF file. So what is this ELF file? Executable and linkable format. This is the file for your PS. So you have machine language for your PS. And what is the machine language for the PL? That will be the bit stream generated in the Vivado. Okay, so that way is already connected with this design one wrapper. Okay, you have the bit stream file in this. Right now we will just run configuration. So as I said earlier, go with this one. So you can see that Cortex is fine, target program FPGA is ticked. So this is the bit stream. From the design wrapper you will get the bit stream for the FPGA part, and for the PS part you will get the application file, app.elf file. Okay, so I'm just running the configuration. Now nothing to verify in the board, so the code will be running in the board. You'll get the multiplied result and that will be displayed in the serial terminal. Meanwhile, let us calculate that value. So you are multiplying FF into FF, right? So yeah, its result is ready. The result is FE01. Okay, let's verify that. Let me open calc. So in the calculator, I need to multiply FF. Okay, so here usually your calculator will be in standard version. You can switch it to programmer so that you can see the hex values. I'm entering the hex value. FF into FF, and the result is FE01. Okay, its decimal value is 65025. So FE01, the result is correct. You have FE01. So that's all about today's lab. Thank you.